All right, chapter 21 is going to be more about carboxylic acids and carboxylic acid derivatives, more about the structure as well as um, the reactions and the synthesis. All right, derivatives, let's talk about some of them. So first you have a carboxylic acid, all right, and then the derivatives are basically you are changing this part of it. You're keeping the carbonyl, but you're changing this part of it. Okay? The acyl halide, more particular acid chloride, Cl is usually a chlorine. I've never really seen a bromine or an iodine there next to an acyl group. So it's usually an acid chloride. Anhydride, we haven't talked too much about anhydrides, but those are carbonyls, oxygen carbonyls. And then you have an ester and an amide and a nitrile. So these are the different acid derivatives. And basically what this chapter is about is interconverting all these compounds into each other. So you can see reactions where you can take a carboxylic acid and you can make an acid chloride or an anhydride or an ester or an amide or a nitrile. You can take an anhydride and make an ester, acid chloride, you can make to an amide, and so forth and so on. So this chapter basically is the reason why this chapter is all these compounds is because all these compounds can be made from each other starting from a carboxylic acid. Okay, esters and amides are commonly found in nature. Amides are found in our bodies. Our amino acids are amide bonds. Okay, esters from carboxylic acids. This is the Fischer esterification. Nothing new here. We've seen this mechanism quite a bit throughout the semester. But esters can be made through the Fischer esterification. We've learned that you can have an excess amount of alcohol or the carboxylic acid to drive the equilibrium. Now let me talk a little about nomenclature for this chapter. I'm going to quickly go over the nomenclature of these different functional groups, but it's not something you're responsible for on the exams. You are responsible for how to name carboxylic acids, but I'm not going to hold you responsible for all of the derivatives. Okay, so I'm going to quickly talk about them just so that you've seen it and you have an idea. Okay, IUPAC names of esters end in O8. Okay, notice all of them end in O8. All right, so basically how you name an ester is you name, there's a common way of naming it and an IUPAC way of naming it. Okay, the parent compound is the part that has the carbonyl. Okay, so this is my parent compound. It's a one carbon chain, so it's a methanoate. Okay, and then this group is named independently from it. Now this is kind of a weird way to do it. I would actually name this isopropyl methanoate since this is an isopropyl group. So that's technically how I would call it. I guess it's a combination of the common name and the IUPAC name. So this would be isopropyl methanoate. So you name the piece that's hanging off of the oxygen first, then you name your parent with an O8 at the end. Okay, so this is phenyl benzoate because that's a benzoate part. Okay, this one is an interesting one. This is my parent compound right here. So this is carbon 1, carbon 2, carbon 3. On the second carbon I have a methyl group. So 2-methylpropanoate, and then the benzyl part is the part in front of it. Okay, so that's how you name esters. Again, I'm not going to hold you too much to the naming, just as long as you kind of understand how to name these. Cyclic esters, we're not going to talk about how to name these, but these are called lactones. A cyclical ester is called a lactone. This will be, if you take a biochemistry course, a molecular biology course, there's a lot of cyclical esters called lactones. All right, so it's a very common name that you'll see quite a bit. Amides, what we'll learn is you basically heat them up in the presence of a carboxylic acid and amine, and you can get an amide. You drive away water. Okay, this is just kind of information. We're really not going to talk too much about it. But basically, amides are interesting compounds. Amides actually exist in this kind of a form. All right, so there's kind of a resonance form in an amide where these lone pairs could pop in, putting the electrons on the oxygen. It's actually been shown that some amides actually exist in this form. Okay, if you notice, this is kind of ionic. Okay, I'm not going to say it is ionic because I don't have a metal, but you do have charges. You have a negative charge and a positive charge, and it makes these compounds very ionic. And because of that, it gives it some very interesting properties. Okay, one type of property is that that the boiling points of amides are extremely high. They're usually solids. If you know your R groups are much larger, you not only do you have hydrogen bonding, if you have hydrogens on the R attached to the nitrogen, but you have this amide part of it. So you kind of have this equilibrium. All right. So in concentrated strong acid is required to protonate an amide. Okay, and protonation occurs on the carbonyl oxygen atom rather than on the nitrogen atom. All right. These are, we've talked about these primary, secondary, tertiary amides, N-substituted and N-disubstituted. That's kind of how we name compounds, which we've learned. Okay, so again, here's some naming. We're not going to go too much into it, but basically it's an amide, ethanamide, that's 2 carbons. This is carbon 1, carbon 2, and you got an ethyl group hanging off of the nitrogen, so N-ethyl ethanamide. All right, again, we've talked about this. I'm not going to stress it anymore. Cyclical amides are called lactams. A lactam, again, this is a name that you might see if you take a biochemistry course. We are not going to, don't worry about learning how to name these. If you're interested, feel free to read, but we're really not going to look into them. Nitriles, we've seen this, hydrolysis of nitriles can give you the carboxylic acid. All right, now if you limit the amount of water you put in there, you can actually stop at the amide. Okay, we haven't really seen that, but it is possible. You can stop at the amide, and then with the addition of acid and water, you can actually go completely to a carboxylic acid. Okay, acetonitrile is a linear molecule. Okay, so to show you it's very similar, if you see the structure of propyne versus acetonitrile, very similar in the structure, except you've got a lone pair. Okay, so if you look in both compounds, the atoms at the ends of a triple bond are sp hybridized, and the bond angles are 180 degrees. So it's very similar to propyne, right? But in place of the terminal hydrogen, that's, you know, they call it the acetylenic hydrogen atom, the nitrile has a lone pair of electrons in an sp hybridized orbital. All right. Oh, and this is interesting, that those non-bonding electrons in the nitrogen are not that strong of a base. Synthesis of nitriles, you form an amide, and then what POCl3 does, we haven't really seen that too much, is that is a dehydrating agent. Dehydrating, or yeah, a dehydrating agent. So what it does is it dehydrates. So it gets rid of a water molecule. Okay, so it gets rid of H2O and it forms it into a triple bond. So POCl3 is a common reagent, to turn amides into nitriles. Naming nitriles, you just end in nitrile. I, without a doubt, am not going to go through this at all, but you basically end in nitrile. Again, it's your parent compound. The interesting thing a lot of people don't realize is that this carbon is part of your parent, okay, which is a little different than other functional groups. So this carbon, so this is a 2-carbon fragment with the nitrile. A lot of people think it's called, you know, like a methane nitrile, but it's actually ethane nitrile. Okay, so that's the only weird thing about it. Alkyl halides, so they show this alkyl bromide. Oh, I don't know how that got there. This acid bromide's not very common. In fact, I have never seen it until right now. Okay, so I don't know what to say. I've never seen them in any papers, in any research. I've never used them, unless it's something that's new that just came out. But I'm really reluctant to say that those actually exist. Okay, but this is a branch of compounds called acyl halides. You can synthesize it from carboxylic acids. We've learned that use SOCl2, so it's a reaction we've already learned. Carboxylic acid, plus SOCl2 will synthesize a chloride. I don't know how you make the bromide, maybe PBr3. I don't know. We'll see if the slides talk about it, but like I said, I've never seen it before. Naming halides, you end in YL chloride. All right, ill chloride. All right, so that's how you name them, and again, depending on how many carbons you have. So you replace the ic acid with YL. All right, it even says acid chlorides are more common. So just to prove to you that that is true. This I don't think so, but who knows? I've never seen that. Acid anhydrides, and hydrides again is a different class of compounds. In this case, you can. It's basically think of an anhydride as two carboxylic acids hooked together. So if you notice, here's a carboxylic acid, hook these together and get rid of water. Notice if you get rid of water, you'll have the anhydride. So, but you can actually cleave an anhydride with water. So two molecules of acid combine with the loss of water to form an anhydride. All right. Anhydrides are more reactive than acids, but less reactive than acid chlorides. We'll talk about reactivity, I believe, in the next section. This is kind of the acyl substitution reaction with anhydrides. Okay, basically your nucleophile comes in, kicks up your electron. This is the tetrahedral intermediate. Okay, we're going to have that in pretty much every single case. And then it pops down and kicks out this whole entire group. Okay, so you have a carboxylate group as your leaving group. So here's the group that you added your nucleophile to. Okay, so a lot of people sometimes they have problems seeing anhydrides react, but it's really not that hard. It's like all the other reactions. You just have that huge group leaving. All right, and it's a good leaving group because it's stabilized through resonance. Anhydrides are named like carboxylic acids, so they end in oic, but instead of oic acid, it's oic anhydride. Typically, they are symmetrical, meaning whatever you have on this side, you have the exact same thing on the other side. Okay, so it's called ethanoic anhydride, meaning both sides are an ethyl group. Okay, trifluoroethanoic anhydride. Okay, now you can have mixed anhydrides, and you kind of name both acids. We don't really have an example of that. Sorry that I keep doing that. Don't mean to keep doing that. Okay, but again, don't worry too much about it. We're not going to stress over it. Okay. When you have mixed groups, all right, multifunctional groups, there are certain preferences. Usually the most oxidized compound is going to get the priority. So you can kind of see that. Remember, oxidized means most oxygens or least amount of hydrogens. Okay, so here and also if it's easy to name, like that's not an easy group to name, but that's a cyano group. Same thing here. This is easy to name. All right, that's a formal group. Also, this is more oxidized because you have a carbonyl and a nitrogen. There's no hydrogens on this one. This one has one hydrogen. Right. The same thing here. This has no hydrogens, but this has a hydrogen on it. Okay, so it's a nitrile. Okay, so again, we're not going to worry too much about this. Don't stress too much about these. Okay. So here's kind of the priority acids, esters, amides, nitriles, aldehydes, ketones. Again, we're not going to worry about that too much. Okay. This is kind of a nice little chart. This is a summary of the nomenclature of everything we've learned through the past 21 chapters. Kind of neat. You kind of can see what everything is. It even has it in the order of priority. Okay, but again, it's based on your what group is more oxidized. Okay. Boiling points. There should be nothing new or different about here. It's based on hydrogen bonding and pretty much what kind of molecule you have. Now, what's interesting here, so if you go up, it makes sense. Alkane is the least. All right, an ester, you could have hydrogen bonding, but you don't have any polar hydrogens, and then a nitrile next. It's because these molecules are flatter. Okay, this has a lot more kinks to it, so we've learned the flatter the molecules, the more it can pack on top of itself. Then you have an alcohol, which has quite a bit of hydrogen bonding. Then a carboxylic acid. Now you have an amide. A lot of people think that these should be switched. Do you think carboxylic acid has more hydrogen bonding than an amide? But remember what I said about the amide? The amide actually actually exists, remember, in this resonance form where you have a negative here and a positive here. So because of that charge on that molecule, it actually has a much higher boiling point than the corresponding carboxylic acid. And you can see it's almost 100 degrees, almost twice as, the boiling point is almost twice as high. Okay, so here they kind of show a resonance picture, how it has a dipole moment, and you really have very strong hydrogen bonds. Okay, so that's pretty interesting.